Hey guys, it's Mr. Mitchell. Today we're going to briefly talk about this concept of power. So just as a quick look back, we did this experiment in lab where we created crash barriers, and what we did was we tried to change the stopping distance of the barrier to alter the force and to keep a passenger safe. In each scenario, however, we did the same exact amount of work, and so we transferred the same amount of energy, even though it was two different circumstances. This car was the same, the ramp height was the same, everything was the same, and so we transferred the same amount of energy. The question is, if instead of changing the distance over which the car was stopped, we instead just changed the time that that stopping occurred. So if we return back to our example from before, where our friend found a bag of money that he was all excited about, and he went to lift it up into the air, right? Let's say he lifted that bag of money and it weighed like 300 pounds or something, and he lifted it in 3 seconds. Versus if he lifted it in 25 seconds. What do you think was a little bit more difficult to do in lifting 300 pounds? You're probably going to say the 3 seconds, right? Because he had to lift it very quickly. So we need to account for this change in stopping time. So how do we do that? Well, power is what we're going to do. So let's revisit this time example with this vocabulary term rate. The rate of change, you've probably talked about this in math a bit, refers to how long something takes. So anytime we're talking about rate, we're talking about time. So since energy and work can change at different rates in a different amount of time, we need something to be able to demonstrate or show that difference, and that something is what we have called power. Okay, so power has to do with this whole concept of time, how long something takes. If we were to define power, defining power is simply, the definition is simply the rate at which energy is transferred, or the rate at which work is done, since they're both the same thing, right? A change in energy or transfer of energy is called work. So power is the rate at which that's done, so kind of how long it takes that change to happen. Power describes how quickly energy is transferred. That's kind of the easier way to put it. So as far as quantifying power, right, we've talked in general, like power is this idea of the rate that the energy changes. If we want to get real specific and then put some numbers to it so we can do some calculations, what we have to do is put it into this equation. Well, anytime we're talking about rate, it's something done in a certain amount of time. Well, we're talking about how much energy is changed in an amount of time. So our power equation is simply going to be power equals how much energy is transferred divided by how long did that take. Since energy transfer is defined as work, an easier way that we can calculate it is just figuring out how much work is done and then dividing it by how long it took to do that work. So P equals, capital P equals W over T. That is going to be our big time power equation that we use to solve problems. So power equals work divided by time. When we're talking about units, remember that work is measured in these units called joules. And time obviously is measured in seconds. So when we try and quantify the units for power, right, we're going to have joules divided by seconds because it's work divided by time. So based upon that formula, we see that it's joules per second. Now we've talked again a million times about how scientists, come up with ways to simplify things, right? Instead of writing joules per second, they said, that's too much work. So we'll define 1 joule per second. We'll call that 1 watt. Right, you've probably heard the term watts before. You've seen it on light bulbs and all kinds of power sources. That is what a watt is. It's 1 joule of work done in 1 second. So when we measure power, we measure it in these units called watts. So when we do a power problem, at the end we'll say it has a certain amount of watts of power. So let's do a couple example problems. The first one is pretty straightforward. Carrie is moving into a new apartment. She does 600 joules of work to carry a box of dishes up the stairs. If it takes her 42 seconds to climb the stairs, how much power did she display? So we always know we want to identify our question. How much power did she display? So we know what we're looking for. In this box, we're going to write our givens. We're given that she does 600 joules of work. So work equals 600 joules. And it takes her a time of 42 seconds to do that work. Remember, we're trying to calculate power, so our equation is going to be power equals work divided by time. As far as our work and solution goes, we're now going to rewrite our power equation. So power equals work divided by time. And then we can replace the work term with the work we got, 600 joules, divided by our time of 42 seconds. So when we calculate that out, we get 14.29 joules divided by seconds. And then we know that in the end we can call that 14.29 watts. So we go to answer our question, carry displayed 14.29 watts of power. So that's a fairly simple example, right? Very straightforward. We're given the two numbers, we have to divide them, and we get our power. But what happens when we're given a problem like this? Tarzan is climbing a tree in the jungle. He maneuvers his 400 Newton body up the trunk a distance of 15 meters. If he climbs the tree in 320 seconds, how much power did he display? So let's go ahead and start writing down givens again. This time, instead of being given the work, we're given that his weight is 400 newtons. So we'll call that a force because weight is a force, right? Force is 400 newtons. Up the tree a distance 15 meters, so our distance equals 15 meters. And then the time was 320 seconds. So things get a little tricky here when we look at the equation, right? Because the equation for power is simply work divided by time. But if I think about this for a second, what is work equal to? Work is the same as force times distance, right? So instead of writing out work, we're going to write force times distance, and we'll still divide by time. Well, look what I'm given. I'm given a force, I'm given a distance, and I'm given a time, and those are the three things I have here. So we're going to solve now just using the force, the distance, and the time. So instead of writing power as work divided by time, we're going to write power as force times distance divided by time. So we'll do that down here. Power equals force times distance divided by time. And then we can just plug in all our numbers. Force is 400 newtons. The distance is 15 meters. And the time is 320 seconds. So when we multiply that all out, we end up getting 18.75 watts. And so we can say Tarzan displayed 18.75 watts of power. So our power calculations are fairly simple and straightforward, nothing as extensive as calculating GPE earlier. We're really just concerned with recognizing that power is displaying how much work is done in a certain amount of time. So it's the rate that work is done. And so there's two ways we can do it. We can either be given the work up front or given the energy change up front, or we may need to calculate how much work is done and then divide it by the time to figure it out. So hopefully this was helpful.